Okay, so for part one of the 6.3 notes, we left off by introducing Kepler's laws. And in this first section, or excuse me, in the second section here, we'll really delve into those in a lot more detail and break them up. So this is going to be new for most of us, so make sure, again, you do follow along. And obviously, if there is anything that's unclear, just let me know so I can help you guys get a further, deeper understanding of this, because it is important that we kind of see where things are coming from and we get comfortable working with elliptical paths and not just the circular paths. Anyway, let's start with just kind of the geometry before we get to Kepler's first law here. We need to start with just kind of the geometry of an ellipse, right? So an ellipse, not being a perfect circle, it doesn't really have a true center. So instead, what it has are 2 points, each of which is called a focus, and the sum of those points, right? So the sum of the distance between those points and the elliptical path is constant. So let's break up exactly what this little paragraph is indicating. So again, we have 2 points, each one is called a focus. So one focus would be somewhere maybe over here, and one focus would be somewhere over here. And the idea of each of those foci is that the distance between either one of these and any given point on the surface. So for instance, if I choose maybe this point up here, well then the distance between this one and that location would be whatever this distance may be, and the distance between our second focus and that point would be whatever that distance is. Okay, so let's call this maybe F1 for focus 1 and F2 for focus 2. Not to be confused, of course, with forces. But anyway, so hypothetically, if this distance was maybe 8 and this distance was 14, then the total there of 22, so 14 plus 8, the total of 22 should be constant no matter what point I choose on this ellipse. So what I mean by that is, let's say hypothetically we choose then another point, maybe somewhere over here. Well, the distance between these points, so if I were to choose then the distance from here to here and the distance from here to here, those totals should also add up to be 22. So maybe this was like a 6 and a 16 or something like that, right? So as long as the total adds up to be 22, then these are the correct 2 foci for the ellipse. So again, a little bit of geometry there with the ellipse. It is kind of important you understand the foundation. Some of the other terms that come into play, right? And I think I gave you most of these on the example page, just to help you out with that. But it is important that you're comfortable with what this is saying. The major axis is the longest distance, which is what we'll determine to be 2a, that passes through the center of the ellipse. So in other words, that major axis is going to go through both the foci. So if I look up here on the diagram up here, I'm going to go ahead and get rid of some of those just so it simplifies the situation a little bit more. So say goodbye to some of those lines there. But anyway, the major axis would be the axis that again goes, it's the longest distance passing through the center of the ellipse. So it would be going straight through the middle there. It'd be passing ideally straight through both foci locations. So the major axis is represented by that. And again, it's defined as a length of 2a. So then the semi-major axis, well, semi is just a prefix that stands for right, half in this case. So it's half of the major axis. So the semi-major axis would be like from the middle of that axis outward, right? And so obviously this portion of that would just be a instead of 2a, right? So just getting familiar with that term. The minor axis, which we won't work a whole lot with in this particular unit here, but the minor axis is the shortest distance. So obviously if the major axis is the longest distance, the minor axis is the shortest distance, the minor axis is going to go vertically in this instance, right? So it's going to go straight down through the middle that way. And we define the minor axis as having a distance of 2b, and then obviously the semi-minor axis would have a distance of half of that, so a distance of just b. So again, just getting familiar with some of the geometry of an ellipse is going to be part of the battle for this third section here of chapter 6, right? So just getting comfortable with some of the terminology and some of the different representations here. So then what does all of this geometry, right, of the ellipse mean for Kepler's laws? Well, it comes back to Kepler's first law, which says, if you go back to read Kepler's first law says that all planets move in elliptical orbits, right? Now, whether they're real exaggerated or not, we'll still see. But the sun is at one of the foci of those elliptical orbits, right? So if this is maybe the orbital path of the Earth or Mars or whatever, then the sun would be at either this location over here. Hopefully that comes out okay there, but the sun would be either at this location or at this location, depending on maybe which planet it is. But the object being orbited around will be at one of those locations. And if the sun would be over here, then there wouldn't really be anything over at this location, right? We would just be following that orbital, that elliptical path around the sun, right? So anyway, that's the significance of some of the geometry in terms of the sun's position and the Earth's position as it orbits around the sun. So anyway, getting pretty comfortable with a situation like that. Before we move on and talk about Kepler's third law, I actually do want to do another example here of something that they use with a lot of these elliptical shapes. Okay, so the thought bubble was the closest I could do to getting another ellipse on there, so let's just pretend maybe those thought marks aren't there, although I know Kenny at this point is probably daydreaming, so maybe a slightly appropriate diagram for this particular situation. But anyway, the other instance I want to show you, and you'll see this a lot when you go through the homework. So again, the first law that Kepler had said that the sun would be located at one of the foci for our elliptical paths. So the sun would be at one of those two locations. A lot of the problems will give you information, though, that's a little bit more indirect in terms of getting to the solution. So what a lot of problems may say is they may say that the shortest distance, so they might tell us the shortest distance between the Earth and the sun is 6.3 times 10 to the, I'm just making these numbers up, but 10 to the 8th. Right? So if that's the shortest distance between the Earth and the sun, then if I think about this elliptical path, well, when would that occur? Well, that would occur over here when the sun is going straight to the shorter part, right, of that major axis. So that distance would be representing that portion. The question may then go on to say, well, the furthest distance, the largest distance between the sun and the Earth would be whatever. So again, I'm just making this number up, but let's say it's maybe 8.7 times 10 to the 8th. So then that would represent the remaining distance of that major axis. So if I asked you then to solve for A or to solve for 2A, right, well, you would just take the largest distance plus the shortest distance, and those together would represent your major axis. So again, your shortest distance plus your largest distance would represent the major axis there. I'll just call this S and L for shortest and largest. Right? So then your semi-major axis, A, which is going to be one of the most important variables that we find as we see through some of these calculations, that would obviously just represent half of that, right? So it'd be S plus, it'd be the shortest plus the longest distance divided by 2, right? So again, a little bit of geometry that ties in with Kepler's first law that we will see is very, very important as we get to some of the calculations for this. So daydreaming aside, this is something I think is worth noting. So again, make sure you're pretty comfortable with it. If you are not, come find me so I can help you get more comfortable with this concept. Okay, so Kepler's first law again said that the sun is at one of the two focus locations for an ellipse. Kepler's second law says that equal areas are covered in equal periods of time. And this takes advantage of angular momentum, which we'll actually come back to later on in the year. So for some of this, I'm actually going to hold off on it. We won't worry a whole lot about this right now, but I do want you guys to get a chance to see what that is saying. And so what that's saying is, we know that again the sun is at one of the two foci locations. So the sun is somewhere over here, and what this is saying is over equal periods of time, the Earth is going to sweep out equal sections, equal areas of this elliptical path. And so again, what that means for us is that if I have, so for instance, maybe during 1 month, right, the Earth maybe moves from this location to this location. So let's say maybe that's the month of January, right? The Earth moves from here to here. Then from the month of February, the Earth maybe moves from here to this location. And then so on and so forth. So, and obviously I'm assuming these months are equal portions of time, which obviously they are not, but let's say instead of months, let's say like 30-day periods, right? So 30 days it goes from this location to this location, and then after another 30 days from here to here, and then after another 30 days from here to here, and so on and so forth. What Kepler's second law says is that the area of each of those sectors would be equal. So as the Earth moves around in its elliptical orbit, it sweeps out equal sectors of area, right? So again, if I was breaking this up into like 12 equal sections, that would represent kind of 12 equal increments for the Earth's orbit. Again, this is going to be something we come back to a little bit more when we have angular momentum. So for right now, the big thing I want you to be comfortable with is what this equation is saying, or excuse me, what this law is saying. And it's just saying that the area of those would be equal as we're elapsing through an equal period of time. So over an equal period of time, you sweep out equal sections of this elliptical path. But that's, like I said, it's not something we'll work with a whole lot right now, so we may come back to this more thoroughly a little bit later on in the year. And then Kepler's third law here says that if you go back to it, it says that the period is proportional, or the square of the period is proportional to the semi-major axis squared. And it's going to be almost identical to the period equation that we developed again from last year. So again, last year we assumed that gravitational force was providing the centripetal force, right? So we said that the universal constant times m1 times m2 over r squared equals mv squared over r. And this is exactly what we saw in the first section of the notes. So I'll go ahead and kind of work through this quickly, but we've actually already seen this derivation once in this chapter, in this section, right? So one of the radii can cancel out, the mass of the object cancels out, so then the orbital velocity would be gm over r. And then when I solve for the period, so again, the orbital velocity would also be equal to 2 pi r over t, because it's following a roughly circular path, right? So 2 pi r would be the distance, and then t would be the time that it takes. So my velocity would be distance over time. So then substituting this in for the orbital velocity and doing a little bit of cleanup, we get t equals 2 pi times the square root of, excuse me, I almost wrote that wrong, of r cubed over gm. Now that's not actually how Kepler first defined this relationship. He actually squared both sides still. So when he first was exploring with this, he left both sides squared. And so what he said was t squared equals 4 pi squared times r cubed over gm. And so really, if you go back to Kepler's third law there, right, if we go back to Kepler's third law, just one more slide back for me, it says the square of the orbital period, which is t, so in other words, t squared, is proportional to the cube of the semi-major axis, which is a, so a cubed. Okay, so we can almost see that with the equation that we just developed, right? This shows us that the period squared is proportional to the radius cubed, right? The distance between the two cubed. Well, this is true for circular orbits. But what we actually see is the same is it holds true for elliptical orbits as well if we just simply change the r and replace it with the a, which is the length of the semi-major axis. So the big one we have for our elliptical equations, the period for an elliptical orbit is, again, t squared would be 4 pi squared times a cubed over gm. So this is why I showed you that little extra section for finding the a, right, finding the semi-major axis from an ellipse. Okay, so it's very, very important when we talk about elliptical orbits. If I want to find the period, I need to find the semi-major axis. I don't care about the specific radius at one location, right? I care about the semi-major axis, which is a. So again, it's half of the major axis. So we need that, and we need the mass of the body or the planet that we're orbiting around, right? And then our universal constant, and we can find our period in terms of seconds. So anyway, very similar to the equation we had last year. Obviously, it doesn't have the square root in there, but otherwise it's equivalent to that equation. But the difference is, instead of the radius, instead of the r, since r is not constant, we need to use this measurement of a. And that's going to be the biggest thing in this first section. This is going to be one of the most new things that you need to get comfortable with, is finding that semi-major axis and using it to help you out. But otherwise, like I said, nothing too crazy in this. So one last note I will make before moving on to the last two examples. So I just kind of left a blank space here, not just to write your name in, but also to convey this. But one last thing I will say is the Earth's orbit actually is very, very close to being circular. The Earth's orbit is one of the closer, in fact, of our solar system. So it's more or less a circular orbit. So even though most of you probably feel like I kind of lied to you last year now, which I kind of did by approximating that it's circular, we will assume that the Earth's orbit is circular unless they tell us otherwise. Okay, so for our purposes, we still actually will assume that the Earth's orbit around the Sun is a close enough approximation to a circle unless they tell us otherwise. So unless they say it's an elliptical orbit, we will work with just it being like the orbital velocity being the square root of gm over r, and we'll work with the orbital period being 2 pi and then the square root of r cubed over gm. Right? So again, we will always work with those equations. That's a terrible r cubed, but whatever. Right? So we'll always work with these unless they tell us otherwise. But anyway, I will finish out the last two examples in part 3 of this video should you guys need it. However, you're welcome to try those on your own if you feel confident with this stuff.